Hello, bachcho, and welcome. Today, we are going to master a very important topic from your Unit 4, Moving Charges in Magnetism. We'll be looking at magnetic force. Now, I know this chapter can feel a little tricky, but I promise you, by the end of this short explainer, you will understand it so clearly that it will be completely exam safe. No more losing marks here.
Okay, so here's our simple roadmap for today. We'll start with a little historical mystery, then understand the main rule behind it. After that, we'll decode the super important Lorentz force formula, apply it to a wire, and then I'll show you 3 common exam traps you have to avoid. Finally, we'll see how this all connects to the bigger picture. Cello, let's begin.
So, let's travel back in time, shall we? We're going back almost 200 years to a moment when a simple classroom demonstration, it sparked a whole scientific revolution. This is where our story really starts. Just imagine the scene, okay? Our professor, Hans Christian Ørsted, is given a lecture. He switches on an electric current in a wire, and a magnetic compass just sitting on the table nearby, which has nothing to do with the circuit, it suddenly twitches. Now, before this moment, everyone, and I mean everyone, thought electricity and magnetism were 2 totally separate things. So what on earth just happened?
And this is what's so incredible. This one simple, completely accidental observation by Ørsted was the first solid proof that no, electricity and magnetism were not separate at all. They were deeply, mysteriously connected. This one lecture demonstration opened the door to a whole new understanding of the universe. Just amazing.
Ørsted's discovery wasn't just some cool classroom trick. It actually revealed a fundamental rule of nature. So let's now unpack the core principle behind what he saw that day.
So the crucial point is this. Look, when a charge is just sitting still, a static charge, what does it do? We learned in electrostatics, it creates an electric field around it. That's it. Simple. But the moment that same charge starts moving, something new happens. It becomes a source of 2 fields. The electric field is still there, of course, but now it also creates a magnetic field. This is the big secret, Bachu. Magnetism is simply a side effect of moving charges.
And this brings us to the exact conclusion from your NCRT textbook, which is what you need to remember for your exams. Ørsted's experiment proved that any moving charge, or a collection of moving charges, which we call a current, generates a magnetic field in the space all around it. This one line is the foundation of our entire chapter. Okay, so moving charges create a magnetic field. Got it. But what happens when a moving charge flies into an existing magnetic field, one that was created by something else? How does it get affected? Well, let's decode the force it feels, which is a very important topic for your numericals.
Right, here it is. This is the famous Lorentz force equation, straight from your book. It tells you the total force on a charge when both electric and magnetic fields are present. But for today, we are focusing only on the magnetic part of this force. So the formula we really need to understand is F equals Q into V cross B.
Now let's break this formula down. First, pretty obvious. The force depends on the charge, its velocity, and the magnetic field strength. Second, and this is very important, it's a vector cross product. Now don't worry about the complex math. For us, cross product just means 2 things. 1, the force is 0 if the charge isn't moving, or if it's moving parallel to the magnetic field. And 2, and this is the most important part, the force is always perpendicular to both the velocity and the field. It's a sideways force.
So how do we find this strange sideways direction? Simple. We use the right-hand rule. Come on, everyone, take out your right hand. Let's do this together. Point your fingers straight in the direction of the particle's velocity, v. Now from there, curl your fingers towards the direction of the magnetic field, b. See your thumb? Your thumb is now pointing in the direction of the force. But be careful, this rule is for a positive charge. If you have a negative charge, like an electron, you do the exact same thing, but the actual force will be in the direction opposite to your thumb. Simple.
Okay, this is great for a single charge. But what happens when we have a whole river of charges flowing together inside a wire? In other words, an electric current. Let's just build on our idea.
Well, the logic is exactly the same. The force on the entire wire is just the total force on all the little moving charges inside it. And this gives us a new, very useful formula. F equals I into L cross B. Here, L is a vector that has the length of the wire and points in the direction of the current. And guess what? You can use the exact same right-hand rule to find the direction of this force too.
Let's look at a very simple example from your textbook to see this in action. A particle moves along the positive x-axis, that's our velocity v. The magnetic field B is along the positive y-axis. Okay, let's use our right-hand rule. Fingers along x, curl them towards y. Where's your thumb point? Along the z-axis. So for a positive proton, the force is along the positive z-axis. And for a negative electron, the force is just in the opposite direction, along the minus z-axis. See? It's very logical once you get the hang of it.
All right, bachcho. Full attention here, please. This is where students often lose marks without even realizing what went wrong. I call these the silent killers. Let's look at 3 common exam traps and make sure you never, ever fall for them.
Okay, the first big trap. So many students think that any force must change the speed of an object. But the magnetic force is special. Because it's always perpendicular to the direction of motion, it can never do any work. Remember, from class 11, work done is FD cos theta. Here, theta is always 90 degrees, and cos of 90 is 0. So the magnetic force is like a guide. It only changes the particle's direction, it makes it turn. It can never increase or decrease its speed or its kinetic energy. Very important point.
Trap number 2 is very basic, but you would be surprised how many people forget it in an exam. Can a magnetic field push a charge that is not moving? Absolutely not. Just look at the formula. F equals Q into V cross B. If the velocity V is 0, the whole force becomes 0. Simple as that. Magnetism is the magic of moving charges. No motion, no magnetic force.
And the third trap is all about direction. It's so tempting to think that the force should be in the direction of the magnetic field lines, right? But that is completely wrong. Remember, the cross in V cross B means the resulting force has to be perpendicular to both of them. The force is always sideways, pushing the particle out of the plane that is formed by its velocity and the field.
Finally, let's just take a step back and see how this one topic is connected to everything else you're learning in physics. This will help you see the whole story, you know.
So in electrostatics, we saw electric field lines start on a positive charge and end on a negative. But magnetic field lines are different. They have no beginning or end. They always form closed loops. This is a fundamental difference. And looking ahead, this magnetic force is the working principle behind amazing things like cyclotrons that accelerate particles, galvanometers that detect current, and the entire phenomenon of EMI. So you see, mastering this is key to unlocking all those future chapters.
Okay, so let's quickly summarize the 5 most important points you must take away from this. 1. Moving charges create magnetic fields. 2. The force on a single charge is Q into V cross B. 3. For a wire, it is I into L cross B. 4. Always use the right-hand rule for direction. And 5. Remember, the magnetic force only turns things. It does no work and it never changes the kinetic energy.
And I want to leave you with this final amazing thought. The great scientist Ampere suggested that even a permanent bar magnet, it's not magic. It's just the result of countless tiny currents circulating inside its atoms. Now, if that is true, what does it tell us about the fundamental connection between charge, motion, and the forces that shape our entire universe? Think about